Yeah, so thanks, David, for the introduction. I'm Brian Wiley from Jülich Supercomputing Center, and with my colleagues Christian Feld and Pavel Savianko, who will be helping out, we're going to introduce you to the Scalasca toolset. I hope that some of you have heard of Scalasca before. Scalasca works with ScoreP, which is the measurement infrastructure that we'll be introducing this morning, as well as Cube, which is the GUI, the presentation tool that we use for presenting profile information. So you'll hear about all of those tools and how they can be used together as they are installed on ARCHER2 and installed on many other systems around Europe and around the world. What we have planned are 2 days for you, today and then continuing on Thursday. So Wednesday's a day off for you to catch up or take a break. We'll introduce the instrumentation and measurement infrastructure ScoreP this morning, and then show you how to look at some of the profiles that we collect with the Cube GUI. And then that should set you up to be able to do some measurements yourself with your own application in the afternoon session. So after the break, which we'll have for lunch between roughly 12:30 to 1:30 UK time, then we'll come back and just go straight into working together to use the tools, either with some of the provided example codes which we have, or your own applications, which is of course much more interesting for us, and I hope much more interesting for you as well. Then we'll come back on Thursday and go into the trace analysis with Scalasca and some additional presentations that allow you to customize things and get more information out of the tools. And to the extent there's also time available, we can look at some case studies together on Thursday. So we have, I think, plenty of time over the next couple of days. We'll try and take things at a relatively leisurely pace. I'm sure that some of you are already experienced and have used our tools before, if not on ARCHER2, but on other systems. But we'll try and take things at a pace where those of you who are not so familiar have a chance to catch up and follow along as well. So although we'll be starting off with mostly presentation here, it's a good time to warn you that you should try and set yourselves up with 2 screens. One where you can actually see the presentation, where we'll also be demonstrating the tools that you can see and follow along with that. But also, if you're going to follow along with the hands-on exercise, you'll need a terminal session. And so this is where you should be logged into ARCHER2, into the account that has been provided for you. And then you'll be able to hopefully follow along and use the tools live as we are demonstrating their use. This is always really challenging if you try and set up 2 screens on a laptop and have to switch between them. So it's really better if you have a second screen. It may be a mobile phone or some other portable device, or if you're lucky, it's a second full-size screen. That will be a much more convenient and comfortable experience for you to be able to follow along with things as we're presenting things and demonstrating. As David already said, we look forward to your feedback, so let us know if we're going too fast, if we need to repeat something, or if something isn't clear. It's always easier to try and explain things at the time rather than come back to things later. But of course, we'll be here throughout the next couple of days to be able to answer your questions, or send us an email if there's something that you want us to follow up with individually. What I'm going to start with is a presentation just of some generic context about performance analysis tools and how they fit into a performance engineering workflow. So performance analysis, parallel performance is not a new problem. It's something that's been around since the very early days. From the first computing machines, there was always a desire to get the machines running more efficiently, to get the applications delivering the results more quickly. And for a long time, you could just sit back and wait for the next generation of processors with faster clock speed, and then you'd automatically get a much better performance. That hasn't been the case for a number of years. For the last years, you've had to do a lot more work on your own, by being able to exploit parallel computing, parallel processing, multiple processors, multiple nodes, each with multi-core processors, often with accelerators. And so you have a rather complex machine architecture to deal with. It's very difficult to get your code, which is itself getting more and more complicated, combining different scientific tasks, different physics and chemistry and all sorts of other things all in one code, working at very different scales, combining lots of libraries and other bits and pieces. So the applications are increasingly complex. The machines where you're trying to get them running effectively are more complex. And it's our experience that every time you go to a new machine, every time you increase the scale, there are new issues that come up that are limiting your performance, a new bottleneck that prevents you getting the efficiency and results that you're expecting from that new resource. There are a lot of factors that come into play in this. There are what we have listed here as sequential factors in terms of the algorithm you're using, how well the compiler is optimizing the code that you have written or that someone has written for you and that you're using for your code. Understanding how that code is using the processor, the memory that's available on that node, the caches that are available to speed up the access to data, the way in which data gets in and out of the node as well. All of these are significant, what we're listing here as sequential factors, of course, but they also affect parallel applications as well. And we're not going to be covering those in any great detail in this course because there's a lot of excellent online training on the ARCHER2 program, either in the archive where there are videos and resources or coming up in the future. So there are different different training events which are listed here, which I recommend that you take a look at and think about using if you need further information in the future. What we're going to be looking at with the tools presented in this workshop are more the explicitly parallel factors. How you have partitioned the code over different processes to run on different nodes, how you might be using threading within a node, and how you use the processes and threads effectively. So how you're doing message passing with something like MPI to distribute data and keep data coordinated between processes, as well as the multi-threading that's going on within a node, within a process, where you also have to deal with how the threads are synchronized, if there's locking required to make sure that data accesses are coherent. So this is these are the sort of parallel factors that we'll be focusing on, where the tools that we'll introduce in the course of the morning will be able to provide insight into your parallel applications and other applications that you might be interested in looking at on other systems or in the future. So successful parallel application performance engineering is a combination of different things where you have to tune different parameters, bring things together in terms of using the right algorithms and libraries. There's a lot of things that may happen automatically, but they won't necessarily be optimal or necessarily efficient. So you have to understand what you're doing, you need to think about what you're doing, and although often it'll be the case things might run, and you might think they're running as you expected, that's often not the case. Often there's a lot of things that are unusual or that are not behaving as you might expect them to be, and so it's important to do some measurements, and those measurements are always better than any sort of guesswork. Those measurements will help you determine where performance issues are. They allow you to do an accurate comparison of different alternatives and validate whenever you make a change that it has the impact and benefit that you're hoping that it did. And of course, this is not something that you can do once and then forget about it. It's an iterative process. Every time you modify things, you change a compiler or change an optimization flag, rewrite the code, use a different algorithm, it's important to go back and do new measurements to verify that the changes are having the impact and benefits that are hoped for. We're not going to be discussing the important area of performance modeling. That's also very important, but it's relatively difficult. It requires quite a lot of experience and quite a lot of insight that you may not have if it's an unfamiliar code. So we're not going to discuss that in this workshop here, but that's another set of workshops on its own where there are other approaches and other tools that can come into play here. But we'll focus primarily on the iterative measurement parts. So we start off with an application which we need to prepare for some sort of measurement. That typically means building it with some debug symbols. That debug symbols will help us to understand what code we're looking at, which source files that code is coming from. It also is an opportunity for us to introduce additional measurement probes. Those hooks will help us get additional information about the code as it's executing. Either this can be done automatically by the compiler or by linking in appropriate libraries, or it may be that you want to do some of this manually yourself to have complete control over it and get additional information that might not be available in any other way. So there's a preparation step which may be simple or can be involve a lot of additional work as necessary. That is then ready to do the first sorts of measurements. In those measurements, we would typically want to figure out what's happening on each process and each thread as the application is executing, aggregate and collect that information together into a high-level summary of the execution, a profile presentation, for example, and then we would capture that in memory and then only write that information at the end of execution. So we're not actually going to the file system and disturbing the execution as in the course of measurement. At the end of measurement, we then have an opportunity to spend much more time on doing a comprehensive analysis. This allows us to calculate additional metrics. We can spend much more time to review the data that's been collected, present it in multiple ways, and help us to identify what are the real performance issues. If you're lucky, everything is executing as expected, but even that's a good result to be able to confirm that things are executing as expected. But if it's not as expected, then the final step of this workflow is to make some modifications and hopefully improve things. These may be simple in terms of just changing the number of processes and threads or running on multiple nodes, or it may mean something a little bit more involved in terms of changing the bindings of processes and threads or changing the code and requiring you to go through this process again. If you haven't changed the code, you can just do additional measurements, but if you're modifying the code, of course, you will have to rebuild it and prepare that new version for the next set of measurements. So this will be an iterative process that may require multiple cycles, and it certainly is something that you will return to in the course of application development. And as you port the application and perhaps use new test cases, every substantial change is something that you'll typically want to come back to and verify it has the benefits that you're hoping for. So that's very high level. We're not going to spend a huge amount of time on it today, and we're not going to recommend that you spend a huge amount of time either, because there's a Pareto Rule which says typically applications spend 80% of their time in only 20% of the code. So if we can identify that relatively small proportion of the code, that's where we would want to spend and concentrate most of our effort. Another aspect of this rule is that if you work on, you'll get most of the results from that effort relatively quickly, and if you spend more and more time to get closer to what could be considered the optimal performance, this will be a matter of diminishing returns. So for most people, if you can get 80% of the benefit with only 20% of the potentially expendable effort, that's a good trade-off for most people. That's a good opportunity to stop there. Only if you're really doing benchmarking or have a real need to get the ultimate performance, will you go back to things and try and get closer to this ultimate performance that might be possible. So the guiding rule here is identify where you can have some benefit, where the code is spending most of its time, concentrating optimizing that, make the common case faster, because the parts of the code that are not the the critical parts, are things that you could certainly spend time improving, but you'll have limited benefit from them. So you can spend lots of time and have relatively limited results as the outcome of that. There are lots of different metrics that we'll cover. We'll focus on a few on the course of this today, and maybe we'll come back and we'll introduce certainly a lot more on Thursday on the second part. But basically they fall into three categories here. We can count how often something happens. This might be how often a function is executed, or how often you do a point-to-point send, or how many sends you're doing, how many receives you're doing from different processes. We can time the duration of those events, how often a function takes to execute, how often it takes to send how long it takes to send a message. So by timing those, we have the duration for them. And in special cases, we'll also be looking at some of the parameters, such as the number of bytes that are being sent, because it should be no surprise that if you're sending more data, that this can have an impact in terms of how long that data takes to transfer. So those are our basic categories: counts in various forms, durations, which will be typically in seconds, but they might be in nanoseconds or fractions of a second, and then things like measures of how many bytes transferred, or maybe how many bytes are written to the file system. From those basic measurements, we can derive additional measurements by converting things to rates: how many times a function is executed per second, how much data is sent per second, how many floating point operations are executed per second. So by normalizing things, we tend to get higher level metrics that might make it easier to compare what's happening on different processes, or different numbers of processes, different numbers of threads, or as we compare different systems. So I've introduced a few basic measurements, basic metrics here, such as the number of times a function is called, or its execution time. More abstract things like the number of CPU cycles that are executed per instruction. That's coming from the hardware which we're executing on. That's very hardware specific. We may be looking also things like floating point operations per second, where again a floating point operation is not something that means the same on two different systems, or means the same thing to different people. There's of course floating point operations that come in different varieties, whether they're single precision, double precision, quadruple precision. Now people often do half precision. So you need to understand what sort of operation you're comparing here, whether it's a hardware instruction, whether it's something that's more at the machine level. As I said, 32, 64-bit variants. There's all sorts of varieties here that need some qualification if you're talking about some of those more specified, more specific metrics. But execution time is typically what you're charged for when you're using a computer system. So that's what you're typically going to be looking to minimize. The faster you can get your results, the happier everyone is, and the less compute resources that you're using as a side effect of that. But just looking at the wall clock execution time is covering a lot of different aspects, including the file I/O, including the memory accesses, other things that are happening on the system, on the nodes at the same time. So if you're sharing a compute resource, this is something that will have an impact on those wall time measurements. On dedicated HPC systems like Archer here, you're going to be using dedicated resources, or we'll be showing you how to use the batch system to use dedicated resources. So whenever you're using a node, it's exclusively reserved for your application. That also means that if you're not using that full node, or if you're not using it efficiently, you're still being charged for that full node, for all of the cores, all of the resources that you're not actually using during that batch job execution. You will still be being charged for. So that's again another good reason to minimize the wall clock execution time. But the CPU time is a measure of how the processes and threads execute. So that's typically a better measure of how you're using that resource. And it won't be including the time where your processes may be switched out for whatever reason, if there are daemons executing on those nodes at the same time, or if you're waiting for file I/O to be done. That's often done in the background by the system. So you may not be seeing the full picture there. So part of the execution time is what might be called user time. It will be system time for file execution, file I/O, and other system operations as well. Often it's the case that execution time is non-deterministic. If that's the case, then you'll have to do multiple measurements to try and figure out what is a representative execution, or add them together to get some sort of average mean execution time. Hopefully that's not the case for the applications that you're dealing with, and it shouldn't be the case if you're doing things with the proper setup of the examples that we'll be looking at in the course of the rest of today. One important aspect which we'll mention in the course of showing our results is the difference between inclusive and exclusive metric values. So in the inclusive sense, we have everything for sub-elements aggregated together into a single value, but we can then typically expand that and then break things down into separate parts. And the part that's left for a specific element is what we would call its exclusive metric value. If we think about the execution time of an arbitrary function such as foo shown on the slide here, the inclusive time would be the time from starting foo to when it returns. So everything that goes on within foo would be part of its inclusive time for execution. If there are bytes transferred, if there's other metrics being calculated, those are inclusive for the entire execution as well. As a distinction, we might be able to measure the time separately for the function here called bar that's being executed, and if we have the values calculated and measured for bar itself, then we can subtract those from foo, and then everything that's left in foo here, in foo itself, which is the part shown in orange, that will be what we would retain in foo as its exclusive metric values. So if we have everything as the inclusive value, it includes the orange and the green part. If it's just the exclusive value, it would be just the exclusive metrics for foo itself. We'll see this in a more concrete case when we come to look at some actual measurements, and I hope the distinction there becomes clear. Other tools refer to this as self metrics, or they have some other terminology, but inclusive and exclusive is the terminology that we'll be using in this tutorial today. So we'll take you through the various steps of doing a measurement and how the measurement data is then recorded and presented and how it's analyzed. But the first step is, how do we actually get the measurements? There are two basic techniques which we can employ. There's a sampling approach or an explicit code instrumentation. If we're doing sampling, then what we're doing is we're periodically executing some additional measurement, interrupting the execution of the application process, which is shown or represented by the timeline here. And as we interrupt it every second or microsecond, then we just take a snapshot of what it's doing at that point in time. So this is using some of the operating system capabilities to get an interrupt. A signal is delivered where we can actually see what is executing at that time. We can, if we're lucky, traverse the call stack and figure out the context of that measurement. And then by aggregating those samples together, we get a statistically representative picture of how many samples were in the different parts of the application execution in the course of the measurement. The nice thing about this is that we typically don't need to do much of a change to the application to be able to get these samples and figure out where they're executing. And by adjusting the frequency of them, we can have a lot of control over how many samples we get, and that relates to how much measurement overhead there is, but also how much the measurement overhead determines how much the application has been dilated by those additional measurements. So if we only have a few measurements, we have a relatively coarse measurement, but if we need more measurements, then we have to accept that there'll be more measurement overhead as a necessary consequence of that. The downside of this is that when we're trying to figure out what's happening in the course of a sample here, so for example something like function sample 6 here, we're in the middle of its execution, and so we can't necessarily tell what's going on or what are the arguments to that function, and we may actually be able to benefit, for example, for MPI operations by knowing how much data they have been sending and received, and that would be a part of the arguments to those. So if we need to get that information, the other alternative is to instrument the beginning and end of each of the routines, and then as the application executes, we execute our additional instrumentation, and that allows us to capture information about the parameters and what's going on. For example, in function foo here, we could actually tell what its argument is, and if this is an MPI routine, then we can figure out how many bytes are being passed in or how many bytes have been received at the end of it. So this requires some additional preparation, but it gives us much more precise information about the precise time when those different events are happening. That's also valuable when we try and compare and relate events from different processes and different threads to figure out how much time they were waiting or spending in synchronization, for example. But for very small routines, it may be if we instrument those, then there's a correspondingly large impact on the measurement. So we have to be a little bit careful in this case to make sure that the routines that we're measuring and the routines that we're instrumenting are really the ones that we benefit from, and the ones which have too much measurement overhead that cause additional dilation are ones we would typically want to avoid. Okay, so we have our precise measurements that we can then process from those. We're not going to specific details about how we do the instrumentation. We'll show you some examples here where we're using the compiler, where we use a preprocessor to process the source code to get the OpenMP events. So we'll figure out where the pragmas are and instrument those. We can also interpose by capturing information from the MPI library. Those are the different formats that we'll show in the course of today. There are other ways to instrument the application and potentially get other information, like doing manual instrumentation of the sources yourself. That's something we'll probably come back to and show you in the second part on Thursday, because it's not critical for getting started today. As I mentioned, there's a trade-off here between how accurate the measurements are based on how many measurements we've taken and the corresponding perturbation that they might occur. There are no measurements that come for free. Every measurement involves having to figure out what's going on. It may be something complicated, like having to traverse the call stack and figure out where the application is executing, or just recording some values from the parameters that have been passed in. All of this can have an impact on the execution time. It will have an impact on the memory accesses, how you're accessing cache, how we're storing things to the buffers where we're storing the measurements. All of those are side effects. And if they're substantial, then this can be a relatively large perturbation of the measurement that we're trying to do, and therefore something we'd like to try and minimize. So a trade-off there between the measurements and the corresponding value that we can get from them. Once we have our measurements, we're going to process those in memory and try and store them before we do our analysis. And so for our processing here, somehow my slides are not progressing, or there's something strange going on. Okay, don't know what that was about, but yeah, so runtime summarization or profiling allows us to take the events as we see them, as the measurement system sees them, and aggregate them together. Either this is adding things together to get the total execution time or the total count, the total bytes transferred for a particular part of the code, or we could be doing something a little bit different in terms of figuring out the maximum or the minimum of those events as well. But mostly we're getting the total, combining things together so that we get, at a glance, we see the total number of bytes transferred, or the total time for specific functions or call paths. A call path is a specific execution context where we can see not just that an MPI operation was done, but we can actually distinguish different MPI operation instances, so that we can distinguish, for example, barriers and send and receive operations in an initialization phase from a more computational simulation phase, for example. And we'll also distinguish things per process and per thread. So this is a rather abstract summarization of the events, but it allows us to minimize how much data we're collecting, and therefore minimize how much memory and how much data we need and process during the measurement itself and after the measurement has been completed. As I said, we have different ways of collecting profiles, and we'll show you examples of those in the course of the rest of the morning here. The alternative is that for every event that we encounter, we can record those in a memory buffer and then process those post-mortem. All of those events, we can timestamp them. We can record their additional attributes, such as the communicator they're using, how much data they're processing, and then all of those events get stored in memory buffers for each thread, each process, and at the end of measurement, we will flush all of those buffers to disk, and then we can do some processing of those. In principle, we could look at them in a trace visualization, or we can do some more sophisticated analysis where we compare the timestamps of events on the different processes and threads to figure out not how much time was spent in those functions, but how much of it was waiting time for the corresponding partner events to be ready to proceed. So that's a chronological ordered sequence of those events stored in different buffers on each processes. They're time-stamped, they go into memory buffers, and then at the end we can bring those together to relate the timestamps of one event with the event on another process or another thread. So that's the most we can do with those. We can then take that information and then do our subsequent analysis of it. The trade-off here is that although we can have a very detailed view of all of the events and how they relate to each other, this is a lot of data, and it very quickly grows with the number of processes and threads that we're dealing with, as well as the duration of the execution, because you can imagine that if you execute 1 million sends, then that's 1 million times more events being collected and processed than if you're just doing a single event. Whereas in the trace analysis, we would aggregate all of those together, and you typically just see a single aggregate event for all of them together. If we can't store everything in memory, if we have to flush that data to disk during measurement, then because those events, those buffer fills and buffer flushes are not synchronized across the processes and threads, this is a substantial perturbation of the execution. So that's why you'd want to avoid, try and avoid if possible, the need of buffer flushes during the measurement itself. If at the end of execution, then we're not so worried about them. Of course, it takes time. They need to go to disk. They will take space on disk. But if they haven't needed to do this during the measurement itself, then we haven't perturbed the data that we were collecting. We'll not do much in the form of online analysis here. That's a complicated business in itself. The analysis that we'll look at is postmodern analysis, where we've stored all of the data on disk, and then we can spend a little bit more time going through that data to analyze it. For the trace analysis, we'll come back to that on Thursday, but that in principle would allow us to visualize what's happening on the different processes and threads, and as I said, relate those events to figure out how much of the time is waiting time. So there's lots of different tools that are available. We're not going to be able to cover all of the tools today. We'll just focus on a few of them that work well together. and then it will be your choice as to how you use those tools. We'll take you through a basic workflow of showing you how what the tools can do, and then it'll be left to you to figure out how those can be used and applied to your application in the course of the measurements that you want to do. There's not one tool that does everything. There's a number of tools that serve different purposes that are appropriate at different points. And as you go from what you need on a single process, a single node, to what you're needing on many nodes, potentially hundreds of nodes, you need to use more comprehensive tools, more powerful tools, and you'll need some advice as to how to apply those. And that's what we're available for in the afternoon sessions, to work with you on your own applications, to give you our advice as to how to best employ those tools with your specific applications on ARCHER2 or on other systems. So the procedure is figuring out if there's a performance problem at all, looking at some basic timing measurements and looking at how those times compare as you try and scale up the problem and use multiple processes and multiple nodes. Identifying what is the key bottlenecks of this application execution. Is it a computation issue? Is it a communication issue? Is it something at the MPI level or something related to OpenMP or threading? And which parts of the application are where the time is being spent? Once we've identified that you have such a problem, where is it happening? Which part of the execution is affected? Is it the initialization or some part of the iterative part of the simulation? We can drill down and try and isolate it to a more specific routine, a specific phase of execution. And then figuring out why is it there? What are the characteristics that it has? It may be that it's something we can look at with hardware counters to figure out, is it a memory access issue? Is it some other aspect of the computation? Or is it something related to the interaction between processes that the trace analysis can be applied to? But the trace analysis is something we'd want to direct specifically to relatively short executions, to relatively small, if possible, numbers of processes and threads, because those will allow us to keep the traces much more manageable. And that doesn't mean that we can't do the trace analysis of very large executions, but if we have to trace many thousands of processes and nodes, the traces will be just that much larger and more complex to analyze. So if we can pinpoint and identify things from a few nodes, then it's always best to start there. And of course, the problems will change as you change the number of nodes that you're dealing with. The scale of execution changes, the amount of work that each process and thread is doing will change. And so those aspects are things where we would want to look at how does the distribution of work, how does the amount of work that's processed by each process of the thread change as you change the number of processes and threads, as you change the number of nodes that you're executing on. We can do this by comparing profiles. We can also, if necessary, compare the trace analysis for this as well. Okay, so that hopefully gives you, those of you who haven't gone through this process before, a little bit more context about what we'll be doing. And I'm happy to answer some quick questions while my colleague Christian hopefully will get set up and ready to go into the next presentation, which will be how to do some initial measurements with SCORP. So, Christian, do I have to stop sharing?
I'm not. Okay, are there any questions to Brian? So there was a question in the chat where to obtain the slides. So they are online already. I paste the link in the chat. So just if you have a slow internet connection, it might be more convenient to to download the slides. Okay, so if there are no questions, then I just start with the next session. So this is about SCORP, which is a measurement system and runtime infrastructure for several tools, for several analysis tools. So Scalasca, Tau, and Vampire. So these tools have different strengths, different weaknesses, but they all share the same measurement infrastructure. So you first need to just a second. Okay, you first need to prepare your code by inserting some extra code, some probes, some hooks, and this is done with a tool called SCORP. And after that, so usually this is done by recompiling and relinking your entire application. So you need to to modify the build system of your application, and we will show you how to do this in a second. So there are several ways to do this. But usually you just prepare you prepend your compile command with the SCORP command, potentially with some options. Then you run the instrumented application. So we are now here, and there we collect performance data. So usually for every thread, we have a large buffer where we collect some data. At the end of the measurement, we aggregate some data. We create a global view of the application. So for example, if there is a function foo on every thread, then the global view will just show a single function foo. And with the first measurement, we can then do some analysis. So there are some command line tools to do some analysis. So for example, we have a tool called SCORP Score, which does some scoring, which is basically a preparation for taking a profile measurement and then looks at what was collected there and make an estimate how much buffer space you will need to do a trace measurement. So trace measurement, as Brian just told you, requires much more disk space than profile measurements. There's also a tool called, or a process called remapping, where we take the raw data, which was collected here at measurement time, and restructure this data. So for example, because we know that you called some MPI functions, that you called some OpenMP functions, and we classify the raw data in a structured way that already gives you, in a profile measurement, already gives you some more information. Okay. Why can't I switch to the next slide? Interesting. Let's see. Okay. So SCORP was started in 2009. So, and it had some history. So there were already some tools existing. So the Scalasca tool set, the Tau tool set from Oregon, and the Vampire tool set from Technical University in Dresden in Germany. And they all came with their own measurement system. So, which was quite unfortunate, because with the own measurement systems, there came different file formats. You couldn't exchange or couldn't analyze data taken with one measurement system with a different analysis tool. So this was quite an unfortunate situation. And therefore, the tool developers of Scalasca, OTF2, Scalasca, Tau, and Vampire teamed up and created a common measurement system that produces data in different formats that can be used with all of the analysis systems. So we came up with two output formats. So one for call path profiling, and here we created the Cube4 data format that is currently used by the Cube GUI, which you will see later today, but also by some modeling tools that are not part of the course here. And then for tracing, we created the OTF2 data format, which is then used by Scalasca and also by Vampire. SCORP is intended to run on any contemporary HPC system, so therefore we support several parallel paradigms, for example, MPI and SHMEM. For threading, we support OpenMP and p-threads, so this also means C++ threads, which are usually based on p-threads. And we also support several accelerator-based programming paradigms. So we support CUDA via the CAPTI library, OpenCL, OpenACC, and since the last version also Cocos. SCORP is open source. We are portable and scalable to all major HPC systems. And so we were initially funded by the German government, but also by the Department of Energy, and somehow on this slide this logo of the Department of Energy is missing here. We further got then also funded by industry, usually, or by other computing sites. So usually to implement some smaller features that were interesting for industry or for this computing site. We from time to time get some patches from users, so we are open source. Everyone can contribute and take the code and extend it, and we are governed by a meritocratic development model. At the moment, we distribute our code as a tarball, but hopefully this year we will open it up and provide a GitLab access to our code. Okay, so SCORP as a graphical overview here. Let me try again if this pointer highlighting works. So the green box here, the large green box, this is your application, yeah. And when we use SCORP to build your application, we insert some hooks, which are the dark green boxes here. So there's, for example, MPI and SHMEM hooks, which are inserted at link time. The thread level hooks partially are inserted at link time, for example, the p-threads one. For OpenMP at the moment, we do some source-to-source translation and recompile the compilation units to insert some hooks. In future, we will change this because of the new OMPT, so the OpenMP tools interface, which will make life hopefully easier for everyone. For the accelerator-based parallelism, so there are different ways to intercept the application. So for CUDA comes with the CUPTI library, OpenACC, and OpenACC I think has an own tools interface. For OpenCL, we do some library wrapping, and Cocos also comes with its own interface. So I/O activity recording is usually done also by intercepting the calls at link time. Then we have the source code instrumentation and different forms of it. So we usually tell the compiler to insert some hooks at every function enter and every function exit. We intercept these hooks then and pass them to the measurement core. There's also a tool called PDT, which comes from the University of Oregon. This can be used to do some source-to-source translation, but basically leads to the same result as the compiler-based instrumentation. Then there are also some user macros that you manually put into your code. This might be interesting if you want to do some very coarse-grained instrumentation, for example, where you just have an instrumentation phase, kernel 1, kernel 2, to get some really low overhead. And here the blue box is a little bit different. So this is sampling, as Brian already mentioned, so where from time to time the application gets interrupted and then collects some data here in the measurement infrastructure. So for all of these boxes, once there is a trigger, we talk to the measurement core. There we augment this event with a timestamp. We store something in a thread local storage buffer. We may augment this event with some hardware counters. So here, for example, we can query the PAPI library, or we can get some RUsage perf or perf counters. In addition, we can also create or hook in some plugins that the user provides. Or, once the event is augmented with some data, we can either pass it to a cube backend, so call or profiling backend, or to the event trace backend. But usually we start with call pass profiles. Which are then can be consumed by several tools. You see the tools here on top. So it can directly be consumed by the Cube GUI, which we will present later today, but also by Tau's Paraprof, which is similar to Cube. We can pass it to a modeling tool, which is called Extra-P. But yeah, to do some modeling, you usually need several cube profiles that are then, so for example, some scaling experiments that are then analyzed by Extra-P to create some performance models. Or you could also put several cube profiles in the Tau database, which is also a tool to do some statistical analysis and some potentially also some modeling. So what we can also do with the cube call pass profile, we can use some command line tools to look into the raw output and to estimate how much buffer space we would need to do or to do a trace experiment. So keeping everything the same, but instead of doing a profile, just do a trace measurement. So this is a process called scoring, which we will also do together later today. Yeah, and the event traces can then be consumed by either Vampire, so you can look at it. So it's a timeline viewer for event traces, or you can do some automatic wait state detection using Scalasca. Scalasca itself, the output of Scalasca itself is again a cube profile that can be used by all of the tools I already mentioned here. What I also want to mention is that with the instrumented application here, or you need to do this instrumentation usually just once. So you rebuild your application once, and then you can do lots of call path profiles or event traces, and also with different configurations. You specify these configurations using environment variables. So this is the Scorpio way of telling the measurement system what to do and which metrics to collect. And this can be done without recompilation or relinking. Now again, okay, I can switch. So these were the original partners who started the project. As I mentioned, we also get some funding from industry to implement some features, or from other computing sites, and we are open for collaboration. So let's start with this process. Before we do any instrumentation, we should do a reference run with our application. So to be sure that everything works as expected. So, and this is what we are going to do now. We have a small benchmark code. We will build it and we will run it on ARCHER2 and check if everything is okay. After that, we have this instrumentation here using SCORP. We run the code again, doing a measurement or a profile collection, and then we start analyzing this measurement using Cube. Okay, let's start with the reference run. So this is based on a small benchmark code here, and we which we use since several years now. It is very portable. This is why we choose it here, and it can be adapted not only to SCORP, but also to other tools that are part of the Virtual Institute High Productivity Supercomputing, so this VIHPS, which is here mentioned on the slides. There are lots of, or you can do lots of exercises with this code, but we will show you here just one way of doing it. So, and therefore we now can log into ARCHER2. We can do this together. So I will show you the commands here in the terminal. I'm not sure if this is large enough, so I can maybe increase the font size a little bit and reduce the size of the slides. So first I log into this training account of ARCHER2. So this is my shortcut here. I need to provide a password. Let's see, I have it somewhere. Okay, now I'm on Archer. So when you log into Archer, you get the default environment, which is I think the Cray, the PROC and Cray environment. But we want to do our examples using the GNU environment. So the issue here is that at the moment there are some linking issues with the PROC and Cray environment, which are already fixed in a new Program Cray version, which isn't shipped on this machine right now. So therefore, we just switch to the GNU environment. So this is done by module restore program GNU. So is this readable on your side? So, or is it okay? Yeah, great. So then we will work from the work file system. So as if you build something on the home file system, okay, you have a big screen. Okay, so I can do it a little bit larger. So there are some issues when compiling some stuff on the home file system and then executing it from the work file system. So to keep things easy, we will do everything from the work file system. So we cd into work, and then we have this group here, this training or TA 031. Again, TA 031, and then just put in your username here. So, and we have a tarball with a small benchmark, and we just extract it here in this directory. The tarball is located also in work in Y23 shared. So here I think you can also find in the tutorial subdirectory, you can also find slides. And so the slides that you are seeing here, they are also on GitHub. So the link I posted earlier. Someone said you can't see the link, so I'm not sure why this is, but you can find the material also from the link for this workshop. There is a materials section, and there you can find the slides as well. So okay, we now extract the tarball in our work directory. Okay. Let's see, here it is. So we then can go into this directory. And so what we are seeing here, it's there are several subdirectories here. So this BT, just a second. So BTMZ here is the directory we are going to use, but there are other benchmarks code in there which are not of interest here at the moment. So it's a it's a benchmark code from NASA. It's freely available, and we use it because it's quite easy to adapt for different systems. It has a very basic build system, if you can call it a build system. So everything is controlled by just a single file. So we will look at this file and change this file a little bit. So it's in the subdirectory config and called make dev. So this is if you want to use this code on a different machine, you need to modify the code. So here, for example, we have this comp flags. As we are going to use the GNU compiler, we want to activate OpenMP using this OpenMP flag. On this machine, we're using GCC 10, which is a little bit stricter regarding the Fortran standard. So you need, or for several codes, you need to add this flag here, fallow argument mismatch. And there's also some fixed line length option that we need to add for the GNU compiler. For the Cray compiler, it would be something different here. Yeah, this is basically this somehow build system. Here we specify the compiler, so the Fortran compiler is a Fortran code. We use FTN here as this is a Cray machine. And here you already see that there are different MPI F77 definitions that we use later, but this is a way basically to modify the compile command to do some instrumentation. But for now, we will leave it as is. Now we want to compile the code. So just try to do make, and then we get some information here. It tells us that there are 3 benchmark names. These are the 3 subdirectories. We are using here the first one, BTMZ. Then you need to specify a class, which is basically the yeah, the size of the of the problem to run. So we are using class C here. We did some testing, and a class C experiment with 8 processes runs in approximately 10 seconds on a node when we're using 6 threads. So for this small example, this is what we need. So to actually build the system, the benchmark, we use this line here at the bottom, and this is specifically configured here for this machine and for this workshop. So class equals C and prox equals 8. So and now we just hit return. Here you see, so the warnings are because of this type mismatch, and we which is now handled more strictly with the GCC 10 compiler, and we switches into a warning using this compiler switch. But you see here that there are several compile codes. So here is a Fortran compiler with an OO3 optimization. Here we have then our flags, this fopenmp, fallow argument mismatch, and this fixed line length none. And here we compile then several Fortran 77 files. In the end, we link the program. This is starting at this line here, and the executable is then built in a subdirectory bin. So let's switch here to. So yeah, what does the benchmark do? So it solves a discretized version of the unsteady compression Navier-Stokes equation, but this is not really important for our purposes here. So for us, it's just a small portable benchmark code where we can easily, which is easily instrumentable for our purposes. Okay, now we want to run this code. So again, it was built in a subdirectory bin here. So we go into this bin directory. We can do an ls, and here it is. So to run it, we need a job script. So we already prepared some job scripts for you. They are in the job script subdirectory, and here we have and other subdirectories for several machines. Here we want to use the ARCHER2 machine. So we also have just an Archer. This was for a workshop last year using the old system. But now we want to use ARCHER2. And for this reference that we are doing here now, we have this run.s batch, and we copy it to our working directory. So here it is. We can look into this job script. So yeah, we use one node. We use eight tasks per node, and we here have the specification for the OpenMP threads. We tell OpenMP how to do the placing, and here in the end we launch the application using the srun. So I'm not sure if we need to use a reservation today. So yesterday, or with the tests, usually the jobs started running immediately. Specify a partition name. So this is new. Can
you show me what's in the job script?
Yeah. Here is a partition.
Partition shouldn't have been commented out. Partition is needed. And then you can uncomment one of the lines for the reservation as well.
So for example, just say this one here.
Yep.
And again, okay. And we look at the status. It's already running. And it is supposed to take approximately 11 or 12 seconds. So it's already done. So, and here we see that it created this slurm output file. Let's look at this file. Yeah, this is the expected benchmark output. So it tells us that this was running with 8 processes and in total 48 threads. It runs for 200 time steps. The verification, the internal was successful. And what is interesting here is that it took roughly 12 seconds. So this is interesting because if you do some instrumentation later on, you introduce some overhead, and you want to keep this overhead in some reasonable range. So therefore, we should keep this 12 seconds in memory and compare it then to our first instrumented run. Okay. So what we have done so far, so we took a small benchmark code and that was easily adapted to this ARCHER2 machine. We compiled it without modifying the so-called build system. We used a predefined or prepared job script to run it on one node. It ran in approximately 12 seconds. So now the next step would be to do some instrumentation using the score-p command. So this means recompiling, relinking the application, and then running it again and specifying or configuring the measurement using some environment variables. So for this to do, we need more software. So we need the SCORP software, and therefore a system-wide module is provided. It's not called SCORP, but Scalasca, and it contains all the tools you need in this workshop. So it contains SCORP, the Scalasca toolset, and the Cube Cube GUI, Cube libraries, and everything else that SCORP and Scalasca depend upon. So let's load this. Module load. Scalasca, and then I think there are 2 versions available at the moment on the machine. So we want to load this newer one here. Oh, sorry, this one here. Not the development version, but the released version, so the default one. So, and now we should have a SCORP and pass. So it's version 7 here. You can also ask for the version using the SCORP version switch. All our tools usually come with a help option. So if you don't know what options to use, then just use the --help one. Okay, so we are still in the source tree of the benchmark. So we go to the top level here. So again, this nothing changed here except that we now have this uninstrumented version in the bin subdirectory. And now we need to modify the build system, so to get the probes, the hooks into the benchmark. And for this, we look again at this configuration file, or this somehow build system of this application, and we don't want to do the usual compilation, so we comment this MPI F77 line here, but we want to do some instrumentation using SCORP. And what you see here is that we prepend the original compile command with the SCORP command and some option to SCORP. So this is the usual approach. You have a compile command, and the compile command comes with some compilation flags. They come from here, and you prepend the entire compilation command with SCORP and some options to SCORP. So this is one way of doing the instrumentation, which works fine if you have such simplistic build systems like here, or just it's basically not much more than a makefile. If you have an application that is built using CMake or the auto tools, then stuff gets a little bit more complex. I think I have something here in the slides. So there's a different option to instrument your stuff, not using not prepending the compiler, but replacing this FTN compiler by a SCORP -FTN compiler and passing in flags to SCORP using this environment variable and passing flags to the compiler using this different this copy wrapper compiler flags environment variable. And we have some slides on this process, so I won't go into detail here, but just keep in mind if you have an easy to modify build system, prepend your compiler. If it's CMake like or AutoTools make like, you need to use these compiler wrappers that we provide and do some more, which we will come to later. But let's go back to our configuration for the VT example here. So we just changed the MPI F77 command, and for this application, that's it for doing the instrumentation part. So we save the file, and then before we do a make again, we do a make clean to get rid of all the old object files. Now, if we do a make, we get the compile command here. So bt z as equals c and prox equals 8. And what we see here is that, yeah, the compile command is prepended by scorp-user, also the link command here. And we end up with a binary in a bin scorp subdirectory here. So we go into this subdirectory. We have this instrumented application. So we can check that it's really instrumented, for example, by using LDD, which shows you that there are lots of scorp libraries are linked into this program. So yeah, we have an instrumental program just by modifying the build system a little bit and recompiling the application. Now we want to run this application. So we use a different job script for this. So it's in the ARCHER2 subdirectory, and it's called p.sbatch. We copy it here into our directory. I think we need to look into it. So we want to have this standard petition, and we want to use this reservation here. So the stuff at the top is, I think, unchanged. What we see here is a section for the measurement configuration. As I already mentioned, the scorp measurement configuration is done exclusively using environment variables. So once you have an instrumented application, you can run it several times in different configurations just by using some different environment variables. I think I have a slide on that here. So you can get a list of all possible, of all usable environment variables for your installation using the scorp-info command, passing the config var subcommand, and the --full gives you some more information about the meaning of the environment variable. So we will look at this command together here in this session. But what we want to do here, we want to use a specific experiment directory. So if you don't specify the name of the experiment directory, Scorp will just name the directory scorpy underscore and then some very long timestamp. So the idea is that subsequent measurements then don't intermix. So, but just having a timestamp is not a very meaningful name. And as we are going to do a summary measurement or profile measurement, we use the sum here as pointing out what we are doing here. Later on, or on Thursday, we will also do a trace measurement. So to keep track of what's in the subdirectory, give it a reasonable name. So we see some other variables here. So for example, this filtering file, we see this a little bit later. Here we have this PAPI metrics. So PAPI is a library to access some hardware counters on the system. Here, for example, is the enable tracing variable that would set the tracing options in scorpy to true, which is usually it's deactivated. So the default is do a profile measurement or summary measurement, and do the tracing only. Or for tracing, you need to do some extra work. So by setting the environment variable. Because you usually don't want to start with tracing because of the trace buffer requirements. So if you do some tracing, you usually also want to specify the scorpy total memory. We will come to this later. So for now, we just set the experiment directory and launch the application as before. So before we do this, we can look here at the scorpy info config vars --full. So it tells us here that we have this enable profiling, and by default it's true. So when we run it just as is, we will do a profile measurement, and the tracing, as already mentioned, is set to false. And there are much more environment variables that are now for the beginning not really of interest, so they have some reasonable defaults. And we just submit the jobs, just setting the experiment directory. Okay, so dispatch scorpy.sbatch. Job is submitted. Let's look at the status. So it's running, and it takes a little bit longer. Yeah, okay. And in the end, it also creates a Slurm output file. Still running, so we wait a little bit for it to finish. Okay. Now it's finished, and we first look into the output, into the Slurm job output, and we again see the output of the benchmark, just as we saw for the reference experiment. We also see that the verification was successful, so luckily Scorpy didn't break anything. And we see here the time in seconds, which is considerably higher than the 12 seconds we saw before. So, but this was a measurement just with the default settings. So we will work on reducing this number here later on. But so far, we instrumented the application. We did the first measurement, and we created some measurement results in this subdirectory, this score PBT, and that's sum. Let's look into this directory. Should be 3 files. So the profile.cubex, this is a raw measurement output. Then we have the score p-config, which is basically a list of the configuration variables that were used. So it's basically the default values of score p except of the score p experiment directory. And we have this manifest file, which gives some meta information about this measurement. So let's look into this file. It tells you what should be in there in this directory. Yeah, so the manifest file, of course, then the configuration file, and the profiling measurement output. It also tells you which variables were used that were different from the default. So this might be interesting if you want to rerun the measurement after a month or so, where you were busy with other stuff, and you can always look into this manifest MD file. You will find the configuration you used in this measurement run, and also which variables you set differently from the defaults. Okay, so now we have this profile.cubex measurement output, which is the raw output, and we could now use, for example, the cube tool to look at the output. There are 2 ways to look at the output. So you can use cube directly, like this here, or you can use do the Scalasca way and using the Scalasca convenience command square, and just pass it the directory. Square would also do some post-processing, the process called remapping that I mentioned briefly. This takes the raw measurement output and looks at the classifications of functions. So, for example, we know that we have some MPI functions, that we have some OpenMP functions, and some user functions, and this process of remapping then reclassifies these functions and creates a tree hierarchy for metrics. So this is done on the fly when you use the square command, but you can also do it manually. Using the cube to remap tool. So we don't do this right now because I think Brian, will you now take over using the showing the cube result of this experiment?
Yes, I can take over.
Yeah. Okay, because so I think I didn't use the I'm not sure if I used the SSH dash capital X, so I'm not sure if I can start cube here at all.
Yes, I mean, so that's what I would propose. We should try and verify that people can start up cube, and then we'll be ready to actually take a short break and come back with that afterwards. So let me.
So I can try to use cube, but I'm not sure if I use the. Okay, now okay, you took presenter and.
Yeah, so I'm hoping that that people actually have their own measurements. If you don't have their own measurements, then please let us know, and then we'll take a look at what the issue is with you. But as a backup, we also have some measurements that we prepared as in preparation for this workshop and just verifying things. So in this directory, work Y23 shared tutorial samples, you'll find a number of measurements, and there's one equivalent to the one that Christian just generated. I already post-processed it, but it's basically the same measurement with a profile in here. So you should be able to find cube on your path, because you should have it's part of the Scalasca module on ARCHER2. So hopefully you find cube, and you should be able to start cube with just the cube command, the directory where this profile.cubex is, and the name of that profile itself. So please try that. If it tells you something about not being able to, there are going to be some warnings which are actually to be expected, but if it doesn't produce a GUI like the one that we're seeing on the right-hand side here, then it's more than likely because you didn't log in with X forwarding or SSH minus Y. So let us know if that's not the case, or configure your X setup so that you can log in and use Cube remotely. For now, that's the simplest thing. If it's still going to be slow, and for me it's certainly responsive enough that I can use it remotely, even though it's in Edinburgh and I'm in Jülich, then the alternative is that you can install the GUI yourself on your laptop, and then you have to copy the files or do an SSH mount to get the files. So that's on this slide here, showing you the two options. One where you can do an SSH-X or an SSH-Y to connect to Archer, load the Scalasca module, and then run Cube. That is the simplest and easiest way. And as I said, if you don't have your own measurement, then you can find it in this directory here. If for some reason that is slow or is not appropriate for you, then you can install the Cube GUI on your own workstation, your own laptop. There are binary packages which you can get from the Scalasca website that I guess I should have put on the slide here. It's not on the slide, sorry. Scalasca.org, and then there's where you can find the packages for macOS, for Windows, or you'll find tarballs which you can then build and install on Linux. If you need some help with that, then send some email to Scalasca at fzjulich.de. That goes to our support list, and Pavel can help you there. Pavel is also, I think, monitoring at the moment, so the quickest thing is, if you're having problems, is to put something into the chat, and then he can set up a session to try and help you there. So as I said, I think for now, even if it's slow, I would suggest trying to use the remote version, which we have installed on Archer. Only if that's an issue, then we'll work with you over the lunch break or in the afternoon to help you get things installed locally, if you need some assistance with that. So I'll leave that slide up on the screen. And as I said, we'll take a break for now, and I would say we start at 12:30 or so that's 10 minutes. Sorry, for me it's 12:30. That's, I guess, 11:30 for UK time. So in 10 minutes we would come back and continue with looking at the profile we just collected, or one of these prepared ones with Cube. Okay, so see you after the break, or let us know if we can help you to get prepared in the next 10 minutes. Okay, I think that we're ready to continue. I see from a number of people that you were able to get your measurements, and hopefully also have the Cube GUI running on Archer. Maybe a little bit slow, but I hope that it's sufficient for at least this first session here. So I'm going to continue with the presentation, which will bring us back to seeing the Cube GUI and what we were what we can find inside this profile. So this section will introduce you to Cube and just show you the basics of how it works, as well as what the basic profile contains. As was already mentioned, Cube is part of the Scalasca set of tools. It provides a number of different components. It provides the GUI, which is the part that we'll be focusing on in this session. There's also some additional utilities for processing the Cube files, the analysis reports, and as well as libraries for reading and writing those files, which can also be used for developing other tools. It's a separate component from ScoreP, but it's something that you need to install with ScoreP, or at least have it installed somewhere. It doesn't have to be installed on Archer or on the system where you're doing the measurement. There's every reason, it's perfectly reasonable to install it on your local system, your laptop and CubeFile laptop or desktop system, and then you can look at the remote measurements collected on some HPC system around the world over some slow connection or whatever. I already showed you this slide. We'll be using the remote connection with SSH-X or SSH-Y, which typically is a little bit faster. To look at the profile that, or a profile similar to the one that Scalasca, that Christian just collected, or you can install it on your own on your desktop system here. Cube is based on 3 dimensions of data, and that's where the name Cube comes from. Those 3 dimensions represent 3 hierarchical axes, 3 orthogonal axes. On the one axis, we have a set of performance properties or performance metrics, things like time, number of visits to a function, number of bytes sent, received, etc. But there can be many more of those. The second dimension is the one here for the different call paths of execution, the different functions of execution, which helps us to isolate and identify the program location where that metric applies to. And the third dimension is the one for the processes and threads, compute nodes. It may include CUDA streams, so things which identify where that code was executing. So those 3 dimensions are presented in Cube as coupled tree browsers, and there are 3 of them. We can rearrange the order where appropriate, but there's basically a set of browsers that where you select something in one, it has an impact, and what is seen in the others. Cube presents the numeric values of the metrics for the different call paths and the locations. It shows them also in a color coding, and the color coding is there to help ease the identification of hotspots or extreme values, perhaps just to identify where everything is balanced, all the colors will be the same. And as I mentioned previously, by navigating through the tree, by expanding and collapsing the nodes of the tree, we can see the inclusive and exclusive values. And then there's all sorts of other customizations that we'll see a little bit later as well. So the basic presentation shown on the slide here is we have metrics on the left-hand side. We have the different call paths or functions of execution in the center pane, and then on the right-hand side we have a representation of the system tree, which is built up of the different processes running on the different compute nodes and the threads of execution, whether they're OpenMP threads or other threads on each MPI process. So that's the basic presentation, and by interacting with this we can explore it and reveal a lot of different data. I'm going to leave the slides at that because I think it's more intuitive if we actually look at things live. So I'm going to switch now to looking at the Cube file that I already have loaded here. So this is just by running Cube on the name of the file, which was in this ScoreP BTMZ sum directory profile.cubex. If you haven't started it with the name of the file, then you'll have a file chooser dialog that allows you to navigate through the file system to find it. But typically it's most convenient if you just start it on the command line. So I hope this is large enough and readable. As I said, we have various metrics on the left-hand side. We'll come back to those. we have the program being shown here in the middle, so this is BTMZ. And on the right-hand side, we have the system tree, where it's showing running on the Cray machine. We're running on a single particular compute node of it, which is this number here, 1450. And then on that compute node, and we were using only one compute node, we have the 8 MPI processes here, ranked 0 to 7. And then if we expand each of those processes, we will see that each of those processes has 6 OpenMP threads. So this is the configuration that we had asked to run and where we got the measurement for. So running 8 MPI processes, 6 OpenMP threads per process. We see the master thread, we see 5 worker threads for those. And when I expand and collapse the nodes here, you'll see that the values change. When it's expanded, I see individual metric values for each of the threads. When I close the node, I get those values aggregated together. Open it again, I see individual values. I can also, by holding down the control or the shift while I'm selecting things here, I get the aggregate value shown at the bottom here. And of course, the aggregate value is the same as the collapsed value. So lots of different ways of showing the same information at different levels in the tree here. Depending on which call path I have selected, these values are going to change. So on the left-hand side, by default, it's showing visits, which is the number of times something has been executed. If I look at the time, this is the aggregate CPU time. What I'm seeing on the right-hand side is now the roughly 40 seconds of execution for each of the threads. And when we have 6 threads aggregated together, we have a number of about 240 as the aggregate CPU time for each process. And if I was to close all of the processes together, then I have the aggregate value for the node or for the full machine. So this is where the 1900 CPU seconds comes. It comes from having 48 threads, each of roughly 40 seconds of CPU time. That's the total execution time. By opening up the call tree in the middle, I can break that down into the different call paths of execution. At the beginning here, I have something called MPI setup, and in the setup, there's the MPI init thread. So I see there's 1 second in MPI init thread, which actually corresponds to about 1/8 of a second on each process. And it's only one of the threads, the master thread, in each process that's actually executing the MPI init thread. At that point, we're outside of a parallel region, so there's no OpenMP threads running. Everything is still being run by the master thread in that case. But we have a master thread for each process. Okay, so having MPI init or MPI init thread at the beginning is what we would expect. There's also some other stuff here for creating and splitting communicators. And at the very end, we have MPI finalize. In this case, MPI finalize is a negligible amount of time, but for an MPI application, we would expect to see the init at the beginning and the finalize at the end. And that's basically what we're seeing in the call tree here. Nothing greatly interesting from those, but what's a little bit more interesting are the other functions, which I don't expect you to recognize because they're application functions, and unless you've looked at this benchmark before, you won't recognize them. There are, of course, things like MPI functions. There's an MPI barrier here, which is used to separate some of the code initialization from the actual timed loop. So we actually see the timer start, timer end for what is the iterative part of the computation. So the part of the benchmark which was timed here is in this region which is marked iteration. Iteration stands out not only by having the largest value, but also because it has the red coloring, and this coloring is according to the color scale that you see along the bottom here. So values which are at the high end are reds and orange, values which are at the low end are blues and cyans, and then you have yellows and other colors in between. So by following that color coding, it helps us to identify where, in this case, most of the time is spent, or whichever metric we have selected. And if I expand the time in the iteration, then I would see inside it there's some sort of exchange routine, as well as the ADI, which is part of the solver here. And inside the solver, we then see it's doing a solve in the 3 directions, X, Y, and Z. And for each of those, there's a parallel region. Inside each of those solvers, there's a parallel region, one for the X solve, one for the Y solve, one for the Z solve direction. And inside each of those, inside the last one, we're also seeing that there's a do loop inside it, and then there's other routines which are being executed inside here. And at the very end of the parallel region, there's an implicit barrier at the end before the execution continues. So you won't actually see the implicit barrier in the code because it's just defining the end of the parallel region. We'll come and look at the source code a little bit later, but basically, I hope you can get an intuitive feel for the code structure here, where we have initialization at the beginning, we have a part which is marked as the computational iterations, and then inside that we have various X, Y, Z solves that are going on, which is actually where most of the time is spent. When I select something from the call tree in the middle, the values on the right-hand side are changing accordingly. So I see that of the 250 seconds of compute time, the exclusive compute time in this case for the OMP do, then it gives me the time for each of the processes and all of the threads here. So they're all taking somewhere between 5 and 6 seconds here, 4 and 6 seconds perhaps. And if I was to select one of the other routines here, then it's all in the 2 to 3 second range. So that's the basic presentation of those values. When I select a different metric, so if I don't want to look at the compute time, if I was to look at the number of visits, this is the number of times that it's executed, then the numbers are changing in all of the panels to the right-hand side. We see that the BT is executed 8 times, MPI setup, MPI init thread is executed 8 times, once by each of the master threads, as we would expect. Things like this iteration is executed 200 times, and if we were to look at the benchmark setup, we would see that it's being executed 200 times. And then within that iterative loop, we're seeing how often these other routines are executed. And some of these numbers are starting to get pretty high. So here we're talking about 100 million, 700 million. That's an aggregate, but it's still roughly 10 million times by each thread, and this was a relatively short execution, so that's perhaps an indicative that these routines are being called a lot, and they're also being called a lot in the other parallel regions as well, because it's the same kind of solve operation that's going on in each of the 3 directions. But here we've actually distinguished what's happening in each of the 3 directions, and if we were to distinguish, I don't know if we'll see it inside here. Here we're seeing the other MPI routines. We're getting much more context information as to where those MPI routines are being called. Rather than just seeing them in aggregate for the whole execution, we're able to distinguish them. These are actually being executed in this exchange routine, where it's exchanging information between the master processes. So again, this is outside of a parallel region, therefore all of the MPI operations in this case are happening by the master threads. As well as the time and the visits, we also have a few other metrics. Interesting ones are things like the bytes sent and received. So if we look at sent, we see here in Exchange QBC, actually I should have mentioned here. So as part of the warm-up for the benchmark, it actually executes the code before it goes into the timed loop. So that's why we're seeing exactly the same routine and exactly the same calls here as part of the initialization, as well as in the iterative loop itself. Here there's only a few calls, a few visits, 7 in this case. That's probably 1 with each of the neighboring directions, whereas down here we have the 200 iterations, and therefore we have many more. We have 200 times the number of sends that are going on here. So when we look at the bytes sent here, we're seeing the aggregated amount of data that is sent. Although the number of sends were the same, the amount of data is different for each process. So this is also indicating that some of the messages are larger than others, depending on how many grid points there are on the neighbor in that specific direction. So when I collapse up this, you perhaps see it a little bit clearer. You see the values that are changing, that are different for each of the processes here. Okay, so I think that's the kind of basic information I wanted to get across at this point in terms of what we have in the profile here. We have some metrics. Currently, there's no structure to them. Here we have the call tree, where we have a lot of structure, some of which we augmented with this iterative marker, but basically we're seeing the different call paths of execution down through the MPI parts and down through the OpenMP. And then based on which metric we select, which call path we have selected for the appropriate metric, we're then seeing a breakdown of that for each process and thread of execution. And that helps us identify not only where the time is spent, but to try and understand why that may be related to the fact that we are sending more messages or larger messages than in other cases. Hopefully, most of you are relatively familiar with MPI or OpenMP, and therefore what you're seeing here shouldn't look too unusual or too strange to you. There are, of course, things that might look strange. For example, if we were to look at where the bytes are received, there are no bytes received in the iReceive. The reason why there are no bytes received in the iReceive is that that's a non-blocking operation. So it's just saying this is an operation we would like to start, we'd like to get that data, but the actual data is actually completed, the data transfers are completed in the wait all that follows. So it's in that wait all is the point where we actually show how much data was received, because it's only at that point we know whether any data was received. It's quite possible that in the iReceive it was never received, it may have been cancelled, or it may have only been partially received. But by the wait all is the completion operation for those non-blocking sends and receives. We know how much was sent because of the iSend has that information, but the iReceive doesn't. It has a buffer ready to collect whatever data is received, but it may only partially use that buffer. So the actual data transfer and its completion is in the iReceive, is in the wait all operation as well. Are there any questions about what we're looking at here, or if people are having problems, then perhaps it's a good point to let us know whether we can continue at this point. I don't see anything, so I think that we've looked at this basic profile, but as Christian pointed out, the measurement took a little bit longer than the 12 seconds we were expecting, and maybe we should try and do a little bit more in-depth analysis, and so Christian will follow up with that to figure out what more we can learn about this measurement before we look at it in a lot more detail, or we look at a new measurement in more detail. So, Christian, are you ready?
Yes, I'm ready. So I share some content. Okay. So yeah, we made our first measurement. So we took the code, modified the build system a little bit, recompiled, and did our first measurement using just the defaults, except for the experiment directory. And we increased the runtime a lot, which might be caused by all these computational functions Brian showed you, which I think some of them were called 2 billion times in total. And we will look into these functions and also the hierarchy of functions to filter out something that is not of interest for us with regards to an upcoming trace measurement and communication or bottleneck analysis using Scalasca. Yeah, so we call this process scoring. So there's an extra tool for this, for looking into the profile and see which functions have how many visits, which functions contribute to the potential trace buffer of a subsequent measurement. What is the time of the functions? What is the time per visit? And we use the Score tool to do this. With this tool, we then create a filter file. So we filter out the stuff that is for our purposes not relevant. So as we're using Scalasca subsequently, we are interested in functions that do some communication and synchronization. So everything from MPI and OpenMP is interesting. But if we have some leaf functions, just doing some computational stuff, we might be not so interested in. So these functions also need to be optimized. But so there you would then maybe use other tools, so doing the serial optimization of small kernels. Okay, let's do this. So I'm here in my terminal. I'm still here on ARCHER2. I'm in the scorpin.scorp subdirectory where we did our first measurement. We use the scorpy score command now. So scorpy score, and we look into the profile that we generated. So this profile.cubex. Okay, here we see some basic information. So if we would do a trace experiment with this configuration, so by just changing one scorp environment variable, we would end up using 159 gigabytes in total. And we would basically have 20 gigabytes per rank, which is way too much, because at the moment this scorp total memory per rank is 4 gigabytes. So this would mean we would have some intermediate flushes, and intermediate flushes means the measurement is disturbed quite a lot because we are writing the scorp internal buffer to disk. I/O usually takes quite a lot of time, so the the timings that we would get with such a measurement are not really useful to do some automatic analysis on this. So we want to have to come up with a buffer size that really fits into memory, so that we don't have to do some intermediate flushes. What we see here in the bottom part is that we have some region or function classification. So we have this all, okay, so everything is in there. Then we have some user functions. We have some OpenMP functions, some COM. So what is this? Then we have some MPI functions and some measurement internal scorp functions. So the COM functions, let's look here at this diagram here. These are yeah, so combined functions. So these are functions in a call tree on the way to some MPI or OpenMP leaf functions. So usually MPI and OpenMP are at the leaf of a call tree, and everything that leads to these leaf functions is classified as combined. So because we are interested in the context where this MPI or OpenMP function was called. So for a subsequent root cause analysis or communication analysis, we are interested in this combined functions as well as the OpenMP and MPI functions. We are not so much interested in the user functions. So, and if we come back here to this data, we see here that the user functions that are they contribute yeah, quite a lot to the buffer size that would be required. That they also in total have 6.5 billion visits, and that they consume 42 or 43% of the total runtime, and that they have a very small time per visit. So this basically means, or it's likely that they contribute or induce a lot of overhead, because so the overhead from scope P or collecting a region event is basically constant. So, and if the time per visit of this region is very low, then the then the overhead, the relative overhead of collecting such a function is quite high. So we can do a little bit more with the score p-score command. We can look at individual functions with the -r switch, so R for region. And I think we should type this through less. So this would give us, or gives us now no, this doesn't work. This gives us all the functions that were recorded in the measurement run. So the top here is as before, but from here on we start seeing the all the functions that are recorded, sorted by this max buff, so this buffer requirements that would be needed for a trace experiment. So, and we see here that we have the top contributors here are the 6 user functions before we get to some OpenMP stuff that we are interested in. So let's see, yeah, this here it's basically the same. So, and these user functions, they contribute more than or nearly 20 gigabytes just for these functions. And we see here that we have 20 gigabytes in total, and this is basically everything goes into these user functions. And here again, the user functions do not contribute to this MPI or OpenMP call path. So these might be candidates to be ignored in a trace experiment. Yeah, so yeah, so we calculated this here so that the user regions contribute 99.6% of the total trace requirements and 42% of the total time. So it's quite likely that if we filter out these functions, that the overhead will be reduced by great amounts, and that we also come up with the trace buffer requirement that fits without problems into the machines or into score P's maximum total memory. Yeah, a filter file. So this was mentioned then several times. So filtering, for filtering, we need a filter file, which is a text file. We have something prepared here for this for this benchmark. So it's in the config directory, and it's called field. So and here we have some keywords. So the Scorpio region names begin, Scorpio region names end. In between these two keywords, we can then have a list of functions to be excluded. There's also an include keyword. Come to this later. But here for this, for the next experiment, we want to just exclude the country or the user function that contributes most to the MaxBuf requirements. So these are the first 6 here, and there's also, I think, this NHS init and timer, but they don't contribute so much. So we can just live with this filter file for the beginning. So how would this filter file now affect a measurement? So it would be interesting to know before you do the measurement how a filter file would work, how effective it would be, and this can be checked again using the score command, using the -f for the filter file, and then just putting the filter file here, scorp_field, and we want to apply this profile measurement. So what you see here is that the total size of the trace is now in the hundreds of megabytes range and not in the hundreds of gigabytes. And then that the Scorpio total memory, so the memory that we need for the event trace per rank, is now 95 megabytes, which yeah, it's an impressive reduction. And here we I think on the top we see the original values, and here we see the reduced values where the plus sign mentions parts that were filtered. We can also do this again with the -r, so splitting it down by region, and here we see the plus sign in front of these 6 user regions, so they are filtered out. And yeah, so with this tool you can also yeah, check if the filter works correctly. So sometimes the filter needs to be, yeah, or the syntax here needs to be, or is quite tricky. So this depends a little bit on the compiler. So for example, here we see some stars, so you can use stars or question marks like in Bash, but we come to this later. So, but here you can then check if the syntax of your filter file does what you intend to do. You can also estimate buffer size if you, for example, want to collect some hardware counters. So hardware counters in Scorpia collected every function enter and every function exit. So this had then additional memory also in a trace. And if, for example, we want to collect two counters, so 2 hardware counters, and want to get this Scorpio total memory recommendation, you can just add a -c and then the number of counters you want to collect. So here, for example, it would then increase the trace buffer size from 95 megabytes to 215, which is still no problem, as Scorpy can collect per rank up to 4 gigabytes. Okay, let's see if we captured everything here. Yeah, okay. So then how to apply this filter. So as mentioned before, in Scorpy, everything or measurement configuration is done exclusively using experiment environment variables. So we would somehow need to tell Scorpy to use this filter file. Therefore, we modify the the drop script. So this was the file scorpy.sbatch. So it's the same as before, but now we need to make some adjustments. So we don't want to write into the same directory again. So we give it a different name. So let's call it Scorpy btmz sum filter. And we need to tell Scorpy to use this filtering file. So we do this by specifying this Scorpy filtering file variable and just point it to to this filter file we just looked at. So and when we run this file, so we take the same binary, so there's no recompilation required. We just do an additional measurement by filtering out the 6 or 7 user functions that we are not interested in and that won't make any contributions for a subsequent Scalasca analysis. And so far, we don't have to specify this Scorpy total memory because this is usually only relevant if you do a trace experiment. But by running this in this configuration here, we would do a profile measurement again, a filtered profile measurement where we can check if the overhead also gets reduced by filtering out these user functions, because this is something the Scorpy score can't tell us. So for this, we need to do an additional measurement. So we store the file, and then we can submit this again. Sbatch scorpy.sbatch. So, and while this is running, we can look a little bit more into this Scorpy filtering. So I already mentioned the keywords here: Scorpy region names begin, Scorpy region names end, and then this to apply the filter, you would need to export the Scorpy filtering file environment variable. So here we filter by region names, but you can also filter by file names. So Scorpy gets the file name usually from the compiler. So when the compiler instruments region enter and exit, it usually provides either an address or it provides the name and the file, the name of the function and the file name. So this depends a little bit of the compiler. So here in this prog and GNU environment, we use a GCC plugin that we provide and that we use during compilation of the binary. And from that, we get all the information at runtime that we need. The advantage is here that we also can apply this filter at compile time. So if you would like to have even less overhead, you could recompile your application and provide the filter at compile time. So this at the moment works for the GCC plugin instrumentation and for recent Intel compilers, and would then need the -- instrument filter option that would then need to be passed to the scorp command. So this here is in gray because it would need recompilation. What we have done here and what's still or hopefully already finished is runtime filtering. So for runtime filtering, no recompilation is necessary, and we see how far we get with it. So yeah, here is an example for file name filtering. So here the keyword is scorp file names begin and file names end, as in contrast to the region names begin and region names end. You still have this exclude and include keywords here, and you see also here this this bash-like wildcards. So you can use these three options here. So you could, for example, also do an exclude star, so exclude everything and then just include few. And so there are unlimited combinations how to specify a filter file. Yeah, same here for this region names. So which we already covered here, for example, is the exclude everything, and then we just include a few functions. So this is also possible. Then the name mangling is a little bit might be a challenge for usually for C++, or maybe also for C. For Fortran, you quite often have an underscore, a trailing underscore at the function names, which you could make portable or a portable filter file by just adding a star. For C++ and C, it's a little bit more difficult, but you can use the output of scorp score to create a potential matching. Here, for example, for the GCC plugin, scorp score would provide this string here. And to match this string, you would need to come up with this string here. This might be a little bit challenging, but you can always use scorp score -f to check if the function you intend to filter is actually filtered, which is quite new. So there's a question. I'm just a second where it is. I miss what the GCC plugin is. Okay, the GCC plugin is a way to do the compiler-based instrumentation. So most of the compilers provide a special switch. So for example, GCC also provides the F instrument functions switch. The Intel compiler provides the -t collect, and then the compiler would instrument callback for every function enter, every function exit. As this GCC F instrument functions is implemented in a way that would introduce much of overhead because every inline function is instrumented, we created a GCC plugin to replace this F instrument functions kind of instrumentation. So basically, it's a different way to get this function enter and exit instrumented. For GCC, there's a way to use a plugin. For other compilers, we usually use a compiler switch. So for Intel, it's -t collect. For Clang-based compilers, there is an F instrument functions after inlining. So there, the inline functions are not instrumented. which is usually what you want, because the inline functions are usually quite short, quite fast, and you would introduce very high relative overhead. Okay, so what's quite new with Scorpy 7? You can generate initial filter files. So instead of writing a filter file by hand, you can just use Scorpy score -g, like here on the slide, which would then take some parameters here, which can be modified, and would create an initial filter file that you can then manually modify. So, for example, let's get this Scorpy score -g. And we always pass it a cubex file. Let's see what happens. So it created this initial Scorpy filter file, and if we look at this, it gives us here the Scorpy region names begin and Scorpy region names end, and it excludes basically the 1, 2, 3, 4, 5. It excludes 5 user files that we also identified by doing it manually. So these are based on the on these buffer percent and times per visit, which is mentioned here. So, but you can specify different values. You can also specify the number of visits. So there are also several ways to create a filter file, and it gives you also more information. So, for example, for this bin vcrhs underscore, it tells you that it comes from this file here. It tells you that it's type user. It tells you the maximum buffer requirements, the number of visits, the time, and the time per visit. So this gives you quite some interesting information that can then be used and to modify this filter file and extend it if necessary. So, and I think it also takes then care of this name mangling here, but I haven't checked this with C and C++. So, but it might already do what you want. But keep in mind that if you switch from one compiler to another compiler, the names here might differ. And yeah, so for example, a filter file generated for GNU might not work as extended as intended on the Intel compiler. So yeah, some time ago we started this filtered measurement run, and we should be finished already. Yeah, we see this file here, and we see it's created this output file. We look at this output file first before we look into the experiment directory. Yeah, so here we have the measurement or the benchmark output as expected, still with a successful verification. And here we see that the runtime was reduced from around 40 seconds to 12 seconds, which is in the range of the original reference run. So this is basically what was our intention here. And if we look now into this experiment directory, we expect to see 3 or 4 files we see now here. We have the manifest, the profile.cubex measurement output, the configuration file, and Scorpy also copied the filter file that was used into this directory for later reference. If you want to run this again, filter is already here, even if the original filter file was moved or is gone. So let's see. Okay, what we have done here is we scored the original or the initial measurement with the high overhead using the tool called Scorpy Score. We saw that there were lots of user functions that were, or there were a few user functions that were called billions of times. They contributed more than 99% to the trace buffer requirements, and these user functions are not of interest when we want to do a Scalasca trace analysis, so finding some root causes, finding some communication bottlenecks, and therefore it was it advisable to filter out these user functions. We did this by providing a filter file. We checked with Scorpy score-f if the filter file is applied correctly. So therefore we then saw a reduced amount of the event trace size and a reduced amount of the Scorpy total memory. We took this filter file, or we used this filter file by exporting the Scorpy filtering file environment variable inside the batch script, and ran the measurement again. So, and the result was reduced runtime, so reduced from 40 seconds to 12 seconds, which we are quite happy with. We could now use Cube again to look at this profile.cubex, which would show you less functions because the user functions aren't there. But the interesting stuff for synchronization and communication, so MPI and OpenMP, is still there. Also the context, so with regards to the call tree. Okay. Before the lunch break, I want to tell you how to deal with measurements with build systems that are not as easy as the one we have seen here. So I mentioned this already, that if you have a CMake based build system or an AutoTools based build system, there is not only the make step, but you usually have 2 steps. You have some kind of configure step, and then you have the make step. And you usually need to provide the compiler or the instrumentation or the prefix to the compiler already at the configure step, because make files are generated, and if the Scorpy command isn't in there, you usually can't do any instrumentation. So therefore we provided some compiler wrappers. So instead of, for example, FTN or CC on Cray systems, we have Scorpy variants of this. So we have the Scorpy FTN for Fortran, we have Scorpy CC for C compiler, and Scorpy capital CC for C++. And we want to provide this to CMake or to the AutoTools configure script already, yeah, for the configure step, so that in the generated make file we then use Scorpy ICC, or here in this example, or ICPC. But at the configure step, we want to have this scorp commands to be inactive, so they don't, they must not do any instrumentation during this configure step. But because sometimes a small test program is compiled by configure, and you don't want to run this, you don't want to create an experiment directory, so you do want to have scorp out of the way. So therefore you need to pass this scorp wrapper equals off before you do call the CMake. Same is true for the configure step of the AutoTools based build system. And then you need to specify the compiler, and you would need to replace your ICC by scorp ICC. So for CMake, you do this using the -CMake C compiler, -CMake CXX compiler flags, and then you run CMake. So then the scorp compiler wrapper is inside the generated make file. But now you need to provide some flags to the when you call make. So you want to have a scorp flag like this --user or this --instrument filter, and you might also want to add some additional flags to the compiler. So therefore we provide two additional environment variables. So for the scorp --user and instrument filter flags, you can use this scorp wrapper instrumenter flags variable. And for additional compiler flags, you use the scorp wrapper compiler flags when you do your make. And then you hopefully get an instrumented application. Let's see. Yeah, that's basically it for this session. Yeah, so you get some further information and also the code to download here at scorp.org. So we have a support mailing list. So if there are any issues, if you have some wishes for new features, just send us an email. There's also a scorp use mailing list where we announce new releases, and you will find a way to subscribe to this list here in this scorp.org. Yeah, so are there any questions? If not, I would suggest that we now go to lunch break and meet again in an hour. Okay, there's a problem with the Cube GUI with the segmentation fault. This might be a question for Pavel. Can you show a line with com? Okay, so the classification. You usually start at main, and then you have some. Maybe I go back here. So imagine that this here is main, and main calls some function foo, and then this function foo calls some OpenMP or MPI here at the leaf. Yeah. Then everything from this OpenMP or MPI leaf up to the top, to the main, would be classified as com, even if it's a user function. If it's just doing some, if it has no own MPI or MPI call, but everything here on the way to main would be classified as com. So to get you the context, otherwise, if we just instrument the MPI stuff, for example, you would just see an MPI sent, for example, but you don't know where it comes from or where it's called. So then, okay, Brian took the presenter.
Yeah, there was one thing I just wanted to show people. It's a little bit of a preview for what's coming up on Thursday, but we already looked at the measurements or saw that we had in the measurement directory a profile. That's what we refer to as an intermediate file or a raw file. And to do the final processing of it, we would use one of the processing utilities, but I'm just going to use Scalasca examine or square, which is the Scalasca extended version of Cube. And I give it the name of the score P directory, which has the profile in it. And what it says is it's doing some post-processing of that profile.cubex. That takes a few minutes, and then once it's ready, it will bring up Cube and show me that new Cube file. At first glance, it might look similar to what we were looking at before, and it should, because there's nothing that we have changed on the right-hand side. We still have the same execution configuration, 8 processes with 6 threads. We've done filtering now, so that's why there's a few less functions that are visible here. So the timing routines, we filtered those out, so there's no longer the timing start, timing end. And if we dig our way down into the solver routines, we'll see that we no longer have a body inside the do loop here. So the purely computational routines that were inside that do loop have now been filtered out, and that's the same for the other ones as well. So that was the main way in which the filtering benefited us in reducing the measurement overheads, but it also, by removing the timer routines, you can think of it as sort of tidying up the call tree as well, because we don't really need to see the timing information for the timing routines. The main thing that the post-processing has done is that it has taken what was a single metric called time, and we now have a hierarchy of metrics here where it's breaking out time into constituent parts. It's breaking it into execution time, and then execution time which is purely computational, and this maps into these user routines. So the purely computational user routines are the ones that would be highlighted when we select computation here. So we filtered a lot of them out. So there's relatively few who are likely to be still here. Actually, I think the purely computational routines, maybe there's something down here. Error norm. That's a parallel routine. The main thing is that things which are MPI routines are now distinguishable because the time in MPI routines is broken out from the total execution time. So inside MPI setup, the time in all of the MPI routines is aggregated together. But the time in non-MPI routines, all of these ones, is now shown as 0. They have OpenMP time. That's not the time for the OpenMP parallel regions, but that's the time for the setup of the OpenMP and the barrier synchronization at the OpenMP conclusion. So these are OpenMP overheads that are now being broken out here. The purely computational parts remain computational. There's computation done in the do loop. There's computation that's done in parts of the setup as well. These are not filtered out. So OMP master time, that's a computational routine, whereas the barrier synchronization is an overhead. So the post-processing done by Square, we're seeing here for the profile. We'll see it later in the week when we look at the trace analysis as well, is taking the basic timing information that's in the profile and splitting it out into the different parts. When we close this tree and are just looking at execution time, we have everything together. But that makes it hard to identify which parts are doing a lot of MPI or which parts are doing a lot of OpenMP or have a lot of OpenMP overhead. Whereas when I select MPI, I'm just seeing the values which are remaining are the values where MPI is used. We see the barrier, we see the weight all, we see the reductions. Within the MPI, we can take that breakdown further and then look at various parts which are going on. So for example, MPI communication, we can split into point-to-point communication, which is this send and receive, collective communication, which is the reduction, and the barrier synchronization is not collective communication, but it's shown up as collective synchronization operation. So this might be a little bit of overkill for a small benchmark code like we're seeing here, where it's relatively easy to identify where MPI is used. But for larger, more complex codes, being able to get this breakdown of the MPI time, the OpenMP time, get the OpenMP overheads broken out into the parts which are barrier synchronization, or here we see there's a tiny amount of critical synchronization, but we can identify where that is very easily because it's down here inside this atomic inside the parallel region is a critical section for OpenMP. So when you're looking at your own measurements this afternoon, of course, you can look at the profile. It has the raw information, but I suggest you look at it with Scalasca, with the square command, and then you'll see these additional metrics which make the whole analysis a little bit easier to navigate and understand. We'll come back and look at this in a lot more detail on Thursday, but I'll wrap up there because I'm conscious that we're running into our lunch break here. Just let me remind you that we'll be continuing after the lunch break at around 1:30. This is flexible. There's nothing. There's no presentation or anything that's scheduled for everyone. You can all just work individually. We'll set up breakout rooms if necessary after the break so that we can discuss with you one-on-one or in small groups if appropriate what you're doing and give you some guided assistance. And we'll have a break as well. I mean, but everything in the afternoon is entirely flexible. But we'll be coming back on Thursday at 9:30 British time, and then we'll continue with the Scalasca trace analysis. We'll look at more of the things that you can customize and augment in ScoreP, and perhaps look at some more things that come out from case studies. So that's what we have planned for the remainder of today. I hope you have a good lunch break, and then you come back and we'll work with you on your own applications as well as with the example codes if you want to prefer working with those. And if there's additional questions that we need to discuss some more, then we can do that as well. I see a question from Oliver asking about file I/O. What would have been shown in the cube file, which I didn't really spend any time was there was a section for I/O there. It'll either be MPI file I/O if you're using MPI, or if you have instrumented the I/O operations at the POSIX level, you'll see those in the tree as well. So that's not something. POSIX I/O is not something that's collected by default. It's something that is some optional instrumentation. We'll discuss that more on Thursday. It's not something you need to need for an initial measurement. There's a question about support for Python. We do have some wrappers for getting information about Python. I'm pretty sure we don't actually have them installed, but those can be installed and made available if you have an application that will use those. So we can follow up with that in the afternoon. You won't necessarily get a lot of information about Python, but you get more information about how the Python code might be using MPI or threading. Enjoy the lunch break, and we'll see you in about an hour's time.